Welcome back. Before we start our deep dive into today's topic, please take a second to hit that like button, subscribe to the channel, and turn on notifications so you never miss a technical breakdown. It really helps the channel grow. Welcome to this deep dive into Apache Ratis. Ratis is an open-source Java library that implements the Raft consensus algorithm, enabling developers to build fault-tolerant distributed systems. Unlike simple replication methods, Ratis ensures that all nodes in a cluster agree on the sequence of operations, even when some nodes fail. This makes it a powerful tool for building systems that must maintain data integrity and availability. It's a core component in projects like Hadoop Ozone and is trusted in enterprise environments for its reliability. In distributed systems, ensuring all nodes agree on the state is critical. Without consensus, data can diverge across nodes, leading to inconsistencies and errors. Consensus algorithms like Raft solve this by electing a leader and ensuring all operations go through that leader. This approach not only maintains consistency but also provides fault tolerance. If the leader fails, a new one is elected automatically, ensuring system availability. This is why consensus is a foundational concept in building robust distributed systems. Let's explore the core concepts in Apache Ratis. A Raft group is a set of nodes that work together to maintain consensus. Each node runs a copy of the state machine, which is the application logic that processes commands. Operations are represented as log entries, which are replicated across all nodes in the group. The leader election process determines which node coordinates the replication. Understanding these concepts is key to leveraging Ratis effectively in your distributed applications. The Raft consensus algorithm is the foundation of Apache Ratis. It's a leader-based protocol where one node coordinates all operations. The leader replicates log entries to followers, and once a majority acknowledges them, they are committed. Raft's design emphasizes understandability, making it easier to implement correctly compared to other consensus algorithms. It also ensures safety through mechanisms like leader election and log matching, preventing data corruption even during failures. Ratis features a modular architecture that separates the consensus layer from application logic. This design allows developers to plug in custom state machines without worrying about the underlying consensus mechanics. The system supports various storage implementations and transport protocols, making it adaptable to different environments. This modularity is key to Ratis's flexibility and its adoption in diverse projects like Hadoop Ozone. Leader election is a critical part of Raft's fault tolerance. When a follower node doesn't receive communication from the leader within a timeout period, it becomes a candidate and initiates an election. The candidate requests votes from its peers, and if it receives a majority, it becomes the new leader. This process ensures there's always a single leader coordinating operations, preventing split-brain scenarios where multiple nodes think they're in charge. Log replication is how Ratis maintains consistency across nodes. When a client sends a request, the leader appends it as a new entry in its log. It then replicates this entry to all follower nodes. An entry is only committed once a majority of nodes have acknowledged it. This majority requirement ensures that even if some nodes fail, the committed entries remain available in the system, maintaining data integrity. The state machine interface in Ratis is where developers implement their application logic. It defines how log entries are applied to the application state. Because all nodes apply entries in the same order, the state machine must be deterministic to ensure consistency. This interface is pluggable, allowing developers to build anything from simple counters to complex distributed databases on top of Ratis's consensus foundation. Client interaction with a Ratis cluster is straightforward but has important nuances. Clients send write requests to the current leader, which handles replication to followers. Read operations can be served by any node, though clients must be aware of consistency requirements. If a client sends a request to a follower, it's automatically redirected to the leader. This design keeps the consensus protocol clean while providing a usable interface for applications. Ratis excels at handling failures gracefully. When a leader fails, the cluster automatically elects a new one, ensuring continuous operation. The new leader continues log replication, and any failed followers can recover by matching logs with the leader. For efficiency, Ratis supports snapshotting, which allows nodes to catch up quickly by transferring a recent state image rather than replaying the entire log. This combination of mechanisms ensures robust fault tolerance. While Ratis provides strong consistency, it comes with performance trade-offs. Latency is influenced by network round trips and disk I/O for log persistence. Throughput is limited by the need to replicate entries to a majority of nodes. However, performance can be improved through techniques like batching multiple requests together. Tuning parameters like election timeouts is crucial for balancing responsiveness with stability in production environments. How does Ratis compare with other consensus solutions? Compared to Paxos, Raft, and thus Ratis prioritize understandability, making implementation and debugging easier. Unlike Zookeeper, which is a separate service, Ratis is a library that can be embedded directly in applications. Compared to Ratis integrates better with Java-based ecosystems. And unlike Kafka, which focuses on streaming, Ratis is purely about consensus for state machine replication. One of Ratis's most prominent use cases is in Hadoop Ozone, where it manages metadata replication for the Ozone manager. This integration demonstrates Ratis's production readiness and ability to handle critical data consistently across large clusters. By using Ratis, Ozone achieves high availability for its metadata, ensuring that file system operations remain reliable even when individual nodes fail. This real-world application shows how Ratis can be the backbone of enterprise storage systems. Setting up a Ratis cluster involves several key steps. First, you define the Raft group configuration, specifying which nodes participate. Each node needs its address and port configured along with information about its peers. You'll also need to implement and initialize your state machine. Finally, starting the nodes with proper peer information allows them to form the cluster and begin consensus operations. The setup process is designed to be straightforward for developers. Monitoring is crucial for maintaining a healthy Ratis cluster. The system provides built-in metrics for tracking leader elections, terms, and log replication status. Monitoring log lag between nodes helps identify performance bottlenecks or network issues. Ratis integrates with standard monitoring tools, allowing operators to track cluster health and performance using familiar dashboards. This visibility is essential for production deployments where reliability is paramount. Security is a critical aspect of any distributed system. Ratis supports TLS for encrypting communication between nodes, protecting against eavesdropping and man-in-the-middle attacks. The system provides hooks for authentication and authorization, allowing integration with enterprise identity management systems. Audit logging capabilities help with compliance requirements, tracking all consensus-related operations. These features make Ratis suitable for deployment in security-sensitive environments. Ratis offers several advanced configuration options for fine-tuning behavior. Election timeouts can be adjusted based on network characteristics and availability requirements. Log retention policies allow balancing between storage usage and recovery speed. The pluggable storage system enables using different backends based on performance needs. Performance parameters like batch sizes and buffer limits can be tuned for specific workloads, making Ratis adaptable to diverse environments. As a Ratis cluster operates over time, its log can grow very large. Snapshotting addresses this by creating periodic state images that replace older log entries. This log compaction reduces storage requirements and speeds up recovery for new or failed nodes. Ratis supports automatic snapshot creation based on log size or time intervals. Finding the right balance in snapshot frequency is important. Too frequent impacts performance, too infrequent increases recovery time. Ratis supports running multiple raft groups within a single cluster, providing isolation between different state machines while sharing underlying resources. This feature is particularly useful for building systems with multiple related services that need independent consensus. For example, a distributed database might use separate groups for schema management and data replication. This approach simplifies deployment while maintaining the benefits of resource sharing and efficient management. In modern microservice architectures, Ratis can be embedded directly into service instances to provide consensus capabilities. This approach enables coordinating distributed transactions that span multiple services, ensuring atomicity. Services can use Ratis to manage shared configuration state, ensuring all instances have consistent views. Additionally, Ratis' leader election can be used to designate primary instances for tasks that should only run on one node at a time, simplifying coordination in distributed systems. When developing with Ratis, several best practices can help ensure robust implementations. First, state machines must be deterministic. Given the same log entries in the same order, they must produce identical results on all nodes. Applications should handle timeouts and retries gracefully, as network issues are inevitable in distributed systems. Proper error handling is crucial for maintaining system stability. Finally, thorough testing of failure scenarios, including leader failures and network partitions, is essential for production readiness. Even with careful design, issues can arise in Ratis deployments. Leader election thrashing, where leadership changes rapidly, often indicates network instability or misconfigured timeouts. Log divergence, though rare, can occur due to bugs and may require manual intervention to resolve. Performance issues might stem from very large log entries that strain network or disk resources. Configuration mismatches between nodes can prevent proper cluster formation. Understanding these common problems helps in quick diagnosis and resolution. The Ratis project continues to evolve with several exciting developments on the horizon. Performance optimizations are ongoing to reduce latency and increase throughput. While currently Java-focused, there are discussions about additional language bindings to broaden adoption. Security features are being enhanced to meet enterprise compliance requirements. Tooling improvements aim to make operational tasks like monitoring, debugging, and cluster management more accessible. These developments ensure Ratis remains at the forefront of consensus technology. As an Apache project, Ratis benefits from an active community of developers and users. Regular releases bring new features and improvements, with contributions from both individual developers and major technology companies. The ecosystem around Ratis includes various tools and libraries that extend its capabilities. Whether you're looking to contribute code, report issues, or simply learn from others' experiences, the Ratis community provides valuable resources for developers at all levels. Apache Ratis is an excellent choice when you need strong consistency in distributed systems. It's particularly well-suited for building replicated state machines where data integrity is paramount. If you're working in a Java-based technology stack, Ratis integrates seamlessly with existing tools and frameworks. And when fault tolerance is a critical requirement, ensuring your system remains operational even when nodes fail, Ratis provides the robust foundation needed for mission-critical applications. Understanding Ratis' performance characteristics is important for capacity planning. In local deployments with fast networks, latency typically stays under 10 milliseconds. Throughput can reach thousands of operations per second, depending on the complexity of state machine operations. Performance scales with cluster size and hardware capabilities, though there are diminishing returns as consensus overhead increases. While Ratis may not match the raw throughput of eventually consistent systems, its comparative advantage lies in the strong consistency guarantees it provides. There are several common patterns for integrating Ratis into systems. The embedded library approach involves directly including Ratis in application services, providing tight integration but requiring Java. The sidecar pattern allows existing applications in other languages to benefit from Ratis by running consensus in separate processes. Gateway services can provide Ratis consensus capabilities to external clients that don't directly implement the protocol. Many successful deployments use hybrid approaches, combining these patterns to optimize for specific requirements and constraints. Running Ratis in production requires careful attention to operational considerations. Backup and disaster recovery strategies must account for both the Ratis metadata and application state. Capacity planning should consider log storage growth and the impact on performance over time. Network requirements are critical, as Ratis's performance is sensitive to latency and bandwidth between nodes. Finally, upgrade procedures need to handle version compatibility and rolling updates to minimize downtime, ensuring smooth evolution of the system over time. Thorough testing is essential for reliable Ratis deployments. Unit testing focuses on state machine implementations to ensure deterministic behavior. Integration testing with multiple nodes validates the consensus protocol under realistic conditions. Chaos engineering techniques can simulate various failure scenarios, building confidence in system resilience. Performance testing under different loads helps understand capacity limits and optimize configurations. These testing strategies together provide a comprehensive approach to validating Ratis-based systems before production deployment. Security best practices are crucial when deploying Ratis in production environments. Always enable TLS to encrypt all internode communication, protecting against network-based attacks. Implement strong authentication mechanisms to control access to the consensus cluster. Regular auditing of access logs and permissions helps detect unauthorized activities. Keeping Ratis and its dependencies up to date ensures you have the latest security patches. These practices form the foundation of a secure distributed system built on Ratis consensus. Effective debugging of Ratis-based systems requires understanding the available diagnostic tools. Log analysis is fundamental for tracking consensus state changes and identifying anomalies in leader elections or log replication. Correlating metrics helps pinpoint performance issues and capacity bottlenecks. Ratis provides tools for inspecting snapshots and logs, which are invaluable for forensic analysis. Integration with distributed tracing systems can provide end-to-end visibility into request flows, making complex issues easier to diagnose in production environments. Scaling Ratis deployments requires understanding several key factors. Cluster size has a direct impact on performance, as larger clusters increase consensus latency due to more nodes needing to acknowledge operations. Multi-tenancy can be achieved through separate raft groups, providing isolation while sharing infrastructure. Geographical distribution introduces challenges with network latency, potentially requiring specialized configurations or hybrid approaches. Proper resource allocation and isolation ensure that different services or tenants don't interfere with each other's performance, maintaining stability at scale. For those looking to deepen their Ratis knowledge, several excellent resources are available. The official Apache Ratis documentation provides comprehensive guides and API references. Community forums and mailing lists offer direct access to experienced users and developers who can help with specific questions. Example projects and tutorials provide hands-on learning opportunities to understand practical implementation details. Conference presentations and case studies from production deployments offer insights into real-world challenges and solutions, helping accelerate your learning journey. Enterprise adoption of Ratis spans various industries, demonstrating its production readiness. Within the Hadoop ecosystem, Ratis powers critical components like Ozone Manager, handling metadata with strong consistency guarantees. Financial services leverage Ratis for transaction integrity in distributed ledgers and payment systems. Telecommunications companies use it for network state management, ensuring consistent configuration across infrastructure. Cloud providers integrate Ratis for infrastructure coordination tasks where reliability is paramount. These diverse adoption stories highlight Ratis' versatility and robustness in demanding environments. Ratis plays an important role in the broader distributed systems ecosystem. Its integration with Apache Hadoop projects like Ozone demonstrates its value in big data environments. Ratis complements container orchestration platforms by providing consensus capabilities that containers themselves don't address. It serves as a foundation for building distributed databases and other stateful services that require strong consistency. Emerging use cases include enabling serverless applications that need consensus without managing dedicated infrastructure, showing Ratis' adaptability to new paradigms in cloud computing. As we conclude this deep dive into Apache Ratis, let's recap the key takeaways. Ratis provides a robust implementation of the Raft consensus algorithm, delivering strong consistency guarantees essential for distributed systems. Its modular architecture enables flexible integration into various applications and services. With production adoption by major technology projects and enterprises, Ratis has proven its readiness for demanding environments. Whether you're building replicated state machines, coordinating distributed transactions, or ensuring fault tolerance in your systems, Ratis offers a solid foundation for achieving these critical requirements. Thank you for joining this comprehensive exploration of Apache Ratis. If this deep dive into consensus algorithms and distributed systems helped clarify how Ratis can strengthen your applications, please give this video a like. Subscribe for more content on system design, distributed computing, and cutting-edge technologies that power modern infrastructure. I'd love to hear about your own experiences with Ratis or distributed consensus. Share your use cases and questions in the comments below. And if you know fellow engineers working on distributed systems, share this video to help them discover the power of Apache Ratis. And that wraps up our explanation. If you found this useful, please hit the like button and share it with a fellow developer. Don't forget to subscribe for more technical tutorials. Thanks for watching, and I'll see you in the next one.